Okay, now we start chapter 10. So first of all, let's get some terminology down. A set is just a collection of objects. Because we're in a math class, those objects are going to be numbers, right? Sets are written with braces. The squiggly ones are braces. So anytime you see something with the braces around them, it's read the set. Okay, so our numbers are broken up into sets. The first set are called the natural numbers. They're also called counting numbers because it's the set of numbers you use when counting, right? So if you started counting, you'd say 1, 2, 3, 4, 5. So this is the set of numbers 1, 2, 3, 4, 5. When you're talking about the natural numbers, you can use a capital N. Okay, then whole numbers is all the natural numbers, so it's 1, 2, 3, 4, 5, dot, 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 plus 0 is in the set. Okay, and we can talk about that with a capital W. The integers are all the whole numbers, so 0, 1, 2, 3, 4, plus the negative whole numbers, -1, -2, -3. Now there's another set that starts with an I. So usually we use a Z when we're talking about integers. Rational number is any number that can be written like a fraction, right? So it includes all of these numbers because I could make all of these look like fractions by putting them over 1, right? So it's all of these numbers plus the other obvious fractions like 2/3, 5.5. But that also includes some of the decimals, right? Any decimal that terminates, has an end, is a fraction, right? Technically, that's 75 over 100, or 3/4. And any decimal that repeats. The most common one that usually people know is 33333 repeating is 1/3. But any decimal that ends or repeats is a rational number. Okay, there's also another R, so rational numbers we usually distinguish with a capital Q. Okay, so far all of our numbers is just the set has grown and added more, right? And it includes all the previous numbers from the previous sets. But when we get to irrational, think about what ir means, right? That prefix means not. So if these are rational numbers, the irrational numbers are not rational numbers. In other words, a number that cannot be written like a fraction. So pi is an example of that. Most people know what pi is, right? Pi is 3.1415, dot, dot, dot. It goes forever. It never stops. Okay? So non-ending and non-repeating decimals are irrational numbers. Another example of that are these numbers underneath our square root signs. That's not square numbers. So square root of 2, right, is 1.414, dot, dot. It just goes forever. Okay, so the irrational numbers, here's our I. And then real numbers. The real numbers are the rational numbers and irrational numbers together. In other words, all of these kinds of numbers, right? So everything we're going to talk about in this course is a real number. Technically, there's one more set called the complex numbers. That's where our I's come in, but we don't talk about the complex numbers in this course. So every number we talk about in this course will be a real number. Okay, so identify the sets to which each of the following belong. 5 is a natural number, right? 1, 2, 3, 4, 5. It's a counting number. It's also a whole number. Okay, it's also an integer. It's a rational number. And they're all real numbers. By the way, I didn't tell you what the real number symbol was. It's not just a capital R. It's a capital R with an extra leg. These capital letters, these shorthands, suffice when we're just talking about sets of numbers, and we know we're talking about sets of numbers. But if you're talking about something else, you really can't just throw in these letters and expect people to know what you mean. But when I write my R this way, right, it's understood to be, oh, that's the set of real numbers. It's just like saying real numbers. Okay, so I could go along right here and just put real numbers on every one of them, right? They're all real numbers. Okay, point 19. It's not a natural number, right? When you're counting, you never say point 19. It's not a whole number. It's not an integer. But since it is a decimal that terminates, in other words, this is the same thing as the fraction 19 over 100. So it's a rational number. And of course, they're all real numbers. Okay, this is obviously a rational number, and they're all real numbers. It's not natural, it's not whole, it's not an integer, right? Okay, same thing here. This is not a natural number, it's not a counting number, it's not a whole number, it's not an integer, it's a fraction, 2 7/10. So it's a rational number, and of course also a real number. Oh, here's that same example we used, 0.3 repeating. Since that is a repeating decimal, I can write it like a fraction, okay? And therefore, it is also rational and real. Okay, this is an accounting number. It's not a whole number, but it is an integer. It is an integer. And it's also a rational number because you can write it like a fraction. So it's also rational and it's real. Another repeating decimal. So it's a fraction. We don't have to know this, but that's 72 over 99. Right? Any repeating decimal we can write like a fraction. So it's rational and it's real. 0 is not a counting number. The natural numbers start with 1, but it is a whole number, right? The whole numbers is 0 is what gets added in to make a different set, whole numbers, and therefore it's also an integer. It's a rational number because I can make it look like a fraction by putting it over 1, and it's a real number. Okay, now let's just try to decide between rational or irrational and explain why. Okay, this is rational. Why? Because it's a repeating decimal, dot, 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 18, 18, 18, 18, right? This is rational. Why? Because it's a terminating decimal, right? This part is 125 over tenths, hundredths over 1,000, right? It's a fraction. Okay, what do you think about this one? It is irrational. And why is because it doesn't end and it doesn't repeat. Look, 202222222220 dot dot dot. I see a pattern that never repeats and never ends. So it's irrational. Okay, let's go backwards here. That's a repeating decimal, so it's rational. This one, because 16 is a perfect square, this number, even though it's written underneath a radical, is actually the number 4. So it's rational. So don't just say, just because a number's under a radical, it's going to be irrational, right? And that's what they're explaining down here, like square root of 9. It's just the number 3. However, if I can't take the square root of the number, it's going to be irrational. Okay, and then you're going to have some problems like this, right, where You're just getting used to what these new, well, they're not new, but just reinforcing what these symbols mean. Okay, 6 is not equal to 1. That's true. 6 is not equal to 1. 9 is greater than or equal to 5. Now, remember, we read math just like we read English in this direction. So when I'm reading across here and I come to the bigger side first, that means I would read it as greater than or bigger than. If I come to the smaller side first when I'm reading, it's less than or littler than. So is 9 bigger than or equal to 5? That's true. Is 8 less than 4? Not true. Is 1 bigger than 2? Not true. Is 6 less than or equal to 6? That is true because of the or equal part. Okay? If either the less than part or the equal part is true, then the less than or equal is true. Now, if it said this, that's false because 6 is not less than 6, but it can be less than or equal to make that one true. Okay, so pay attention with your signs, right? If you need to go back and forth between the less than and the greater than, you got to make sure that the numbers also switch. In other words, the little side of the sign needs to always point towards the little number wherever it happens to be. And the big side needs to point towards the big number. Okay, and then parentheses. We've used parentheses for a lot. It means multiplication if you've got a number written right next to a parenthesis or a parenthesis right next to a parenthesis, right? If we need to separate signs and we have a negative number, we use parentheses to separate the signs so they don't blur together, right? Or we use it for the order of operations. Now we might start seeing double parentheses. And if we do that, we might want to use brackets in place of one of the sets of parentheses, just to avoid confusion, right? For example, here, where now I know that this side goes with this, right? Okay, and then these two go together. So I got to do inside parentheses first. And if I have parentheses inside parentheses, I got to do the innermost ones first. So everything else is going to stay the same. 8 plus 3, but 6 plus 5, I can do that. That's just 11. Now when I'm working inside these parentheses, there's more than one operation, and we got to do multiplication before addition. So that's 8 plus 33. Still working inside the parentheses. So this is 2 times, what's that going to be, 41, which is 82. Okay, since there's nothing inside the parentheses to do, remember, we distribute. And this means negative 5 times 3 times A, or negative 15A, and negative 5 times negative 4, positive 20. Okay, looking inside the parentheses, these are not like terms. You can't combine them. Same thing over here, not like terms. So our other method for getting rid of parentheses is that distributive property, right? 5 times 2a squared is 10a squared. 5 times negative 6a is negative 30a. Now I've got minus 3 times 4 times a squared, so minus 12a squared. And minus 3 times minus 9 plus 27. Okay, now here's an a squared and here's an a squared, so I can combine those. 10 a squareds, take away 12 of them, would give me -2 of those a squared things. Okay, I don't have another one that's just an a, so it has to stay. And I don't have another constant, so it also will stay as is. Okay, can't do what's inside the parentheses, so we distribute. -2 times 2 is -4 times y, and -2 times +3, -6. Okay, that wraps up this one. See you next time.